Hello and welcome to this second lecture in the series of high frequency amplifiers. We are discussing the BJT at high frequency, and today we are going to discuss about the derivations of resistive components which are present inside the hybrid pi model and how they are related with each other. So the outline of today's lecture is interrelationship between hybrid pi model and the H parameter model. Hybrid pi model we draw for the high frequency analysis of the amplifier, but it does not mean that we cannot analyze the low frequency amplifiers by using this hybrid pi model. So today we will see that how hybrid pi model can be modified to analyze the amplifier at low frequency also. Okay, and another thing is very important. We already studied about the H parameter model in case of the low frequency analysis of the amplifier, and today we are also going to see how the pi model is related with the H parameter model, the conventional H parameter model that we study in case of the low frequency amplifier. Then we will derive the derivations of transconductance GM, then rb'e and rb'e. Then we will discuss about the outcomes and the question related to the today's lecture. Let's start. So this is the pi model which we discussed in the previous lecture. We are at the module 2, and I am in the second lecture of the module 2, that is the high frequency amplifier. And in earlier lecture, in the first lecture, I discussed about this hybrid pi model in detail, and we came to know that this capacitances CC and CE, diffusion and transition capacitances, are the part of the hybrid pi model essentially because they represents the high frequency analysis. When we analyze the high frequency, when we analyze the transistor at high frequency, then we need not and we cannot ignore the presence of the capacitances, the internal capacitances. So these values represents the high frequency analysis of the BJT. Now what if I have to analyze the BJT at low frequency by using the same hybrid model? Okay, that is the pi model I am talking about. We have been studying about the H parameter model in case of low frequency analysis, but we can also use the hybrid pi model for the analysis of low frequency. And how we can do that? We have to simply remove these two capacitances from here, and the model will be applicable for the low frequency also. Okay, so likewise we can draw this diagram. Yes, this is the diagram. So I have removed the two components, that the two capacitor components. First is the diffusion capacitance and second is the transition capacitance. And here when we draw this diagram, this is the diagram of hybrid pi model at low frequency. So the only difference between the low frequency and high frequency analysis in case of the hybrid pi model is, if we consider the capacitances value, then we say that the model is applicable for the high frequency, and if we ignore the capacitance value, then we can say that the model is applicable for the low frequency. Yeah, but since we have already calculated the H parameter model, we have to relate the hybrid pi model with the H parameter model so that we can find out the interrelationship. And why we are interested to find out the interrelationship? Because all these components which are present here, that is the rb'e dash, that is the rb'e, rb'c, okay, GM, RCE, all are interrelated with the low frequency parameter model of the H parameter. Yeah, and we can derive all these things by using the HIE, HOE, HRE and HFE value. Why we do this? Because we already know the values of HIE, HOE, HRE and HFE at the ideal condition. So since engineers and scientists have already measured these values, and manufacturer regularly use this value, it is the frequently used values across the world. If we configure the transistor, if we are manufacturing the transistor, then the HIE, HOE, HRE and HFE, that is the H parameter model, H parameter values are very well known and distributed across the world. So if I am modeling the pi model for the low frequency, then I can easily relate that pi model of low frequency to the H parameter model that already exists. It will help me for the analysis. So just for the sake of the simplicity, we are going for this. Okay, so you can see that this model we draw for the common emitter transistor in case of the H parameter model, and how these two diagrams are interrelated. We can see that in place of HIE we are using rb'e dash, okay, and in place of HOE here, in place of HOE we are using the RCE here. Similarly, this rb'C and this rb'e is related with HFE and HRE. Okay, how it is related we will see when we will go through the derivations. Let me revise one thing for you, because we are discussing about the low frequency H parameter model and we are interested to calculate the components which are present in the pi model by using the H parameter model. Then it is important to just revise the H parameters equations which we already studied in case of the common emitter transistor. So this is the H parameter equation, the popular H parameter equation. V1 equals to H11 I1, H12 V2, and I2 equals to H21 I1 plus H22 V2. Which configuration I am talking about? I am talking about the configuration of common emitter, and when we talk about the common emitter configuration, we can see that VBE is my V1, means the input voltage, IB is my input current, that is I1, and similarly VC is my output voltage, that is V2, and IC is my output current, that is I2. So I can just replace the value of V1, I1, V2 and I2, and I can get these two equations. So these two equations are derived from here, and we have just replaced the values of common emitter parameters here. And now if I want to calculate the HIE, what is HIE? HIE is VB upon IB when I put this VC value as 0 as written over here. Similarly, I can calculate the value of HRE, I can calculate the value of HFE, and I can calculate the value of HO. Okay, these things are already clear in case of the low frequency analysis, so I am not going into the detail of this. And as I already told you in the previous slide, that the rb'e dash is related with the HIE, RCE is related with the HOE. Here these two things, rb'C is related with the HRE and rb'e is related with the HFE, that we will discuss when we will come across the derivations of these two components. So let's begin the derivation of transconductance GM. See, without deriving the equation of transconductance GM, we cannot derive the other equations. Why? Because every other component is related with the other component. They are interrelated in terms of the analysis, and the first important component is GM. Why? Because whatever input voltage we are providing here, I am talking about this, the first diagram, whatever input voltage we are providing, that is VB dash E, that is certainly generating the current IC at the output, and GM relates me between this VB dash E and IC. GM relates me between this VB dash E and IC. So we have to first derive the value of the transconductance, and then we can derive the other resistive components and capacitances also, which are present in the hybrid pi model. Okay, so let's move ahead. And what is GM? GM for me is change in the collector current upon change in the base emitter voltage. So DIC upon dVB, or del IC upon del VB dash E, you can also say like that. Now we know that why we are concentrating at this equation, because ultimately we have to replace this IC and VB dash E value, and we have to somehow find out the way to relate this collector current with the input voltage. So this collector current IC, this is the output equation of the common emitter transistor. If you remember this, IC equals to alpha IE plus 1 plus beta ICO, where ICO is the reverse saturation current. Okay, we can ignore this value because reverse saturation current is the very small value, and ultimately alpha IE will give me the solution for the IC. So IC is equal to alpha I. Okay, so differentiating the above equation with respect to VB dash E, because why we are differentiating? Because we ultimately want to calculate the value of change in the IC with respect to the value of change in the VB dash E. So I'm going for the differentiation. When I'm differentiated, I will get this kind of equation. And since this is the constant value, we can ignore its presence and it becomes 0. ICO is the reverse saturation current. It is the constant value. Beta is also the constant value. Very small values. Okay. Now moving ahead, IE is equal to IO into e to the power VB dash upon VT minus 1. This is the diode equation. Which junction we have written this diode equation for? The first junction between the base and the emitter. So the input current can be written like this. Now why we are taking this particular equation? Because here we have the term IE, okay, and here we have differentiated IE with respect to VB dash E. So somehow we have to calculate the value of IE, and we want the value of the IE so that it could be replaced in the above equation. Now moving ahead, if I expand I just expanded the previous equation, opened the bracket, and again differentiated with respect to VB dash E. Why I have already told you, because here we have the term in equation number 2 del IE upon del VB dash E. So I have to again differentiate the above equation with respect to VB dash E. So this kind of equation will appear for me. Sorry, this is the equation which will appear for me. And here when I look at this equation carefully and go here, so I naught plus IE will give me the ultimately this value. Yeah, so I have replaced this value as IE plus I naught from the above equation. Okay, and since I have replaced this value, I can easily say that I naught is going to be very less than IE. What is I naught? I naught is again the reverse saturation current. Don't be confused. This has come from the diode equation. I naught into e to the power VB dash E and all. So I naught is nothing but the reverse saturation current. So this reverse saturation current is going to be less than IE. Now when I replace this value, I get this IE upon VT here, because I am ignoring the value of the I naught. Again from equation 2, if I see, where is the equation 2? This is the equation 2. In equation 2, if I see this value we have already calculated, del IE upon del VB dash E. How? From here, del IE upon del VB dash E can be written as IE upon VT. So from equation number 2, if I replace this value del IE upon del VB dash E, I can get this value. So del IC upon del VB dash E equals to alpha IE upon VT, and alpha IE upon VT. See, IE equals to alpha IE upon VT. Where it has come from? It has come from here. Since we can ignore this value, so IC can be replaced as alpha into I. So likewise we have replaced these values, and alpha IE can be written as IC from equation number 1, and we have calculated that how GM is related with the output collector current. So GM is nothing but change in collector current with respect to change in the input voltage VB dash E. So IC upon VT is the parameter which gives me the value of the GM. Okay, so from equation number 2 and equation number 1, use these equations and get this value. Now we are interested in calculation of the input resistance, that is the rb'e dash. As I have already told you that rb'e dash is related with HIE, written over here also. So HIE is the parameter, the input impedance, which is related directly with the rb'e dash. What is HIE? HIE is VBE. Let me say VBE or VB dash E. Let it be VBE. VBE is the voltage which is present across here. VB dash E is present across here, and there is a resistance in between them, rb'e dash. So this is the VBE which is present across the input of the whole circuit, and this is VB dash E which is present across the rb'e dash. So applying the KVL, simply we have applied the KVL at the input loop. So if you apply the KVL at the input loop, you will get this kind of equation. VB is equal to rb'e dash into IB plus RB dash into I. Okay, IB is common. So we have calculated the value of VBE, and this VBE value can be substituted in the above equation. So if we substitute the above equation, then we get this kind of value. So IB can be cancelled out, and we get this value HI equals to RBB dash plus RB dash E. We are interested to calculate RBB dash. So what is RBB dash? RBB dash is nothing but HIE minus RB dash E. So this equation ultimately gives me the requirement of another derivation, that is the RB dash E, because if we do not know the value of the RB dash E, we cannot calculate the value of the RBB dash. So we are directly moving towards the calculation of the RB dash E. So what is RB dash E? RB dash is related with the HFE. Here I have written RB dash E is related with HFE. See, by looking at the diagram, you cannot directly predict that how RB dash E is related with the HFE. If you carefully look at this particular circuit, the relation is indirect. VB dash E is the voltage which is present across RB dash E, and VB dash E is the same voltage which is responsible for this current source. Okay, and what is this current source? Current source, this is representing me the value of the IC. So VB dash E is the value which is giving me the value of the IC. And how this VB dash E is formed? VB dash E is formed by this input current multiplied by this resistance. So ultimately the VB dash E, which is related with the collector current IC, it is giving me the interrelationship between IC and IB. Is it not? Okay, so what is IC upon IB? IC upon IB is nothing but current gain, that is HFE. So this is the indirect relation that RB dash E is related with HFE. So we have to use the equation of the HFE for analyzing the value of the RB dash E. I hope this is clear with you. For you. And the IC, what is HFE? HFE is IC upon IB when I put VCE equals to 0. Yeah, and when we further analyze this circuit, we can see that this RB dash E is nothing but the feedback component. Why it is feedback component? Because it is relating the collector to the base terminal, and collector is my output and base is my input. So any component which relates output to input, that is known as the feedback component. So RB dash E is the feedback component, and we can just apply the Miller theorem to separate this feedback component into two parts, as we already do in case of the low frequency analysis. So this is the first part which comes for me. This is the Miller 1 resistance, and RM1, you can say this is RM1 Miller resistance first, and this is Miller resistance second, which is come across here, RM2. So here I have separated this resistors into two parts, RM1 and RM2. The rest circuitry is same. Okay, because unless we separate this resistance, we cannot go for the further derivation. So we have done it. And now since we have said already that VC is going to be 0, okay, because we are interested to calculate the value of the HFE, so I have to ultimately find the value of the K. What is K? K is output voltage upon input voltage. So what is output voltage here? Output voltage is VCE and input voltage is VB dash E. So now I am not taking the value of the VBE as we have done in the previous case. Now I am taking the value of the VB dash E. This is important. Why I am taking the value of the VB dash E? Because RB dash E is present across VB dash. VB dash E is present across RB dash E. And we are interested to calculate the derivation of the value of the RB dash E. Yeah, so VC upon VB dash E gives me the value of the K, that is 0, because VC is 0, and we can see from the diagram that I naught is nothing but minus IC. You can see here IC and I naught at the output. RCE is holding the value of the I naught, and IC is flowing across the internal terminal. So IC and I naught is the opposite value. So I am not taking the I naught value, I am just taking the IC value. Okay, I am not writing in terms of I naught, I am just writing in terms of IC. So IC can be written as GM into VB dash E. That is the equation number 1. Now we can see from the figure that RB dash E at the input terminal, RB dash E and RB dash C upon 1 minus K are in the parallel. So we have to go for the parallel calculation, and in the first lecture I have already told you that RB dash E is measured as 1 kilo ohms and RB dash C is measured as 4 mega ohms. These are the standard values which we have discussed in the first lecture. Okay, so this comes out to be as rb'e. Why? Because when we analyze the transistors, analyze the resistors in parallel condition, always the lower value comes out to be the approximate value for the overall analysis. So if you just analyze the parallel values of 1 kilo ohms with 4 mega ohms, ultimately the answer comes about the value of 1 kilo ohm. So we are ignoring the value of the rb'e and taking the value of the rb'e. Okay, so what is VB' then? VB' is nothing but IB into RB'. We have already calculated that. This is VB'. VB' is nothing but IB into RB'. So if you multiply these two things, you can get the value of the VB', which is present across here. Okay, so I have replaced the value of the VB' here from equation number 1. I can say that the VB' value is replaced, and I am getting the value of the ICS GM into IB into RB'. So I know that HFE is nothing but IC upon IB. Okay, so I just transfer this value here, and I can get the value of the IC upon IB, and IC upon IB can be written as GM into RB'. So what is IC upon IB? IC upon IB is nothing but HFE. So HFE is equals to GM into RB'. So ultimately, if you want to calculate RB', comes out as HFE upon GM. Or if you represent it in terms of conductance, since conductance is opposite of resistance, so we have just reversed this equation, and we can get the GB' equals to GM upon HFE. Okay, so that's all for the today's discussion on the derivation of GM, rb'e and rb'e. So we have seen that how the hybrid pi model is interrelated with the low frequency H parameter model, which we derive in case of the low frequency. And by using the hybrid pi model, you can also analyze the low frequency amplifier. But since we are very well known with the H parameter model of the transistor at low frequency, so we have to interrelate to calculate the value of the resistive components. So today we have calculated the value of rb'e and rb'e by knowing the value of the GM. Okay, so you can be asked in the examination that draw the hybrid pi model at the low frequency by removing those capacitances and calculate the value of GM, rb'e and rb'e. So this is the discussion of today's lecture, and in the next lecture we will see how the other two components rb'c and RCE is going to be calculated. Thanks for watching.